Okay, good afternoon once again. Our topic for today is about the physics of bipolar transistors. So I'm Engineer Febus Reidj Cruz from the School of Electrical, Electronics, and Computer Engineering of Mapua University. Okay, so let's start with our discussion. So on the physics of bipolar transistors. So these are the topics. So we'll learn about the structure of bipolar transistors, the currents and voltages of bipolar transistors. Then we'll have the large signal or DC, direct current model of bipolar transistors. Then we'll have the characteristics of bipolar transistors. And then finally, we'll have the small signal, or this should be AC model of bipolar transistors. For the details, you can read the chapter 4 on physics of bipolar transistors in our textbook, which is the Microelectronics by Professor Razabi. And the expected outcome for this topic is under course outcome 1. That is to make use of bipolar transistor device models and use it to solve and analyze bipolar amplifier circuits. So in this lecture, we'll be able to learn about the bipolar transistor device models. So let's start with the structure of bipolar transistors. So all of the semiconductor devices are actually fabricated using a silicon wafer. And the typical type of material of a wafer is a P-type semiconductor substrate. Okay? So if we take a look at one of the die or chip in a wafer and look it in a microscope, then we can see this kind of structure. So you may notice a large area which will serve as the collector region. And inside the collector, you can notice a different type of semiconductor which will serve as the base region. Then inside that base material, we'll have another diffused layer which will be the emitter region. So this will show the three regions of bipolar transistors. So as we are all familiar, bipolar transistors are made of three terminals or three semiconductor regions. So namely collector, base, and emitter. Now here is the layout and cross-section of NPN bipolar transistors. So when we say layout, this is more of a top view. So when you look from the top of the wafer, again, we can notice a three rectangular, concentric, rectangular, or square structures. So the largest structure will be a collector. Then inside it, you'll have the base. Then inside the base region, we'll have the emitter. For an NPN bipolar transistor, collector will be made of N-type. So usually in representing layout of semiconductor devices, we use color green to represent an N-type. Then we use yellow or orange to represent P-type material, and another green for the emitter to represent the N-type. So this will be an N-type emitter, P-type base, and an N-type collector. Then, if we will add the contacts and the metal layer, so this will be the layout view of bipolar transistor. So on top of the collector region, we'll have the multiple contact cuts. Then on top, we'll have the aluminum metal layer. Then the same with the base, we have a multiple contact cuts and the metal layer. And then for the emitter, for this particular drawing, we have a certain area for the emitter that it can only accommodate a single contact cut. Now, if we cut through the middle, this will be our cross-section line. So we can now see the side view of the bipolar transistor. So again, the body or the substrate will be P-type. And then through the cross-section, we'll have the collector region. So this will be the N-well. So that would be the collector region. And on the side, you have the contact cut. And on top, you have the metal one. So the contact cut represents the opening through the insulation layer, connecting the metal layer and the semiconductor layer. So you have two contact cuts representing the collector terminal. Then another region would be the base region, which is a P-type. So again, you have two contact cuts for the base terminal. And inside the P-type, you'll have another N-type. So this time we designate emitter as N+. So whenever you see a cross-section drawing showing an N+, that describes a high doping concentration. So the emitter region of bipolar transistors are heavily doped. So whenever you represent or draw the layer, make sure to add a plus sign indicating the high concentration of the region. Okay? Then you have a single contact cut for the emitter. Now, normally for our textbook, we simplify our cross-section of NPN bipolar transistor. So instead of showing this complete type of cross-section wherein you show the substrate, then you have the N-well, P-type, and the N-type, we can just indicate the N+, then the P-type, and then the N-type. So normally we simply represent three layers. So this could be the three layers wherein we indicate the emitter terminal, base terminal, and the collector terminal. So on the right side, we now have the simplified layers of NPN bipolar transistor. So again, you have N+ for the emitter, P-type for base, and then N-type for the collector. Okay, so is it clear so far? Please confirm.
Yes, po, sir.
Yes po, sir.
Okay, thank you. So for the bipolar transistors, we have two types. We have the NPN bipolar transistor, and we also have the PNP bipolar transistor. So the name or the type of bipolar transistor describes the semiconductor layers. So the NPN is descriptive that you have an N+, P-type, and N-type. Then for the PNP, you have the P+, N-type, and the P-type layers. So the middle layer is the base terminal, and the other side would be the emitter and the collector. So again, the emitter, whenever we represent a drawing, again, always indicate the plus sign, which means high concentration, high doping concentration. And when we draw the collector, make it obvious the collector region having the largest area. So normally when I draw the bipolar transistor, I would actually exaggerate a large area for the collector. While base will have the lowest doping concentration, and at the same time will have the smallest area among the three regions. Okay? So again, let me repeat. Emitter has the highest doping concentration. Base has the lowest doping concentration and the smallest area. While collector will have the moderate doping and the largest area. Now, before we continue, let me show you an actual example of bipolar transistors in a circuit. So here is what we call a CMOS band gap reference circuit using bipolar transistors. So based on the schematic diagram, the circuit uses PNP transistors. So this is actually my first one of my first integrated circuit that I designed and have fabricated. And I was able to publish this in the first ever journal of ICEP. Now, looking at the bipolar transistors, when we draw the layout, so how are we going to implement this schematic diagram into integrated circuit? So we are going to convert the transistors into their equivalent layout drawings. So for the bipolar transistors, take note of the concentric squares. Again, you have the largest square as the collector. Then inside that, you have the base. And on the middle, you have the emitter. And if you count the bipolar transistors, these are actually 10 PNP transistors. Now, if you look at the schematic diagram, it only shows 3 PNP transistors. And the reason is transistor Q2 is actually made of 8 parallel transistors. So Q1 is actually on the middle part, surrounded by 8 transistor Q2. Then Q3 would be this one. Okay, klaro ba yun? Is that clear? Please confirm.
Yes po.
Yes, sir.
Sige. And then after drawing the layout, you'll submit this to a foundry or the fabrication house, and we're able to fabricate the circuit. So ito yung actual photo nung IC natin, no? Integrated circuit. And on the actual chip or die, ganito na yung appearance ng bipolar transistors. Okay? So ganyan ang itsura. Now, for the bipolar transistors, we have 4 operating conditions. So let us consider an NPN transistor. Again, the emitter is made of medium size N+ heavy doping layer. Then base would be made of smallest area, low doping P-type. Then the collector will have the medium doping but large area collector region. Then based on the layers, we'll have 2 PN junctions. You have a PN junction between base and emitter. So we can call it base emitter PN junction. And another PN junction between the base and the collector. So bipolar transistors have 2 PN junctions. One on the base emitter and another one between the base and collector regions. Now, having 2 PN junctions, with every PN junction having 2 possible biasing, we can either forward bias or reverse bias the PN junction. So we'll have 4 possible conditions. The base emitter and the base collector can be forward biased and reverse biased respectively, or they can both be forward biased, or the 2 can be reverse biased at the same time. And the last possible condition is base emitter is reverse biased while base collector is forward biased. Now, when we forward bias the base emitter PN junction, that will provide a very thin depletion region, and that will result to a lower input resistance. That will result to a lower PN junction resistance between the base and the emitter. And then when the base collector region is reverse biased, that would result to a wider depletion region, resulting to a higher PN junction resistance. So in this setup, when we forward bias the base emitter PN junction, we will provide a lower input resistance, while when we reverse bias the base collector junction, we will have the higher output resistance. So when a current from the emitter, so kaya ang tawag sa kanya emitter, sa kanya nanggagaling yung mga carriers, no? So doon nag-originate yung current natin. So when the current from the emitter passes through a lower input resistance, that would result to a lower input voltage. So by virtue of Ohm's law, voltage is directly proportional with the resistance. Now, when the same current passes through a higher resistance, that will result to a higher output voltage. So take note that most of the current from the emitter will exit through the collector. So almost 95% to 99% of the emitter current will go out as collector current. So we can assume that the current passing through the input junction will be almost the same current that will pass through the output junction. Okay? So yan na yung condition that will be able to establish when you have forward bias and reverse bias condition. And if you notice, this will result to a voltage amplifier. You have a lower input voltage turned into a higher output voltage. So by having forward and reverse bias condition, bipolar transistor can behave like a voltage amplifier. Is that clear to everybody? Please confirm.
Yes po, sir.
Yes, po, sir.
Okay, thank you. So this kind of operation is what we call the active operating condition, and the application of bipolar transistor will be as amplifier. Now, when both junctions are forward biased, we call the operation as saturation, wherein the internal resistances will be very, very low, so the transistor will behave like a closed switch. While when both junctions are reverse biased, the internal resistances will be very, very high, and so the bipolar transistor will act like an open switch. Then for the final condition, we call it as reverse active, wherein instead of as amplifier, the transistor will act like an attenuator. So you have a higher input voltage becoming a lower output voltage. So we call it as attenuator application. Now going back, we want our bipolar transistors to be operated in the active mode. So again, electronics 2 focuses on the amplifier applications. So the requirement for our bipolar transistors should be in the active mode. So again, bipolar transistors in the active mode requires that the base emitter junction must be forward biased to set up a low internal input resistance, and the base collector junction must be reverse biased to set up a higher output resistance. So for an NPN transistor, in order to forward bias the base emitter, we have to apply positive voltage on the P-type side base and negative voltage on the N-type emitter. So that means the emitter voltage, not necessarily negative. So this means the emitter voltage must be smaller than the base voltage. And normally, when we forward bias a junction, the typical voltage drop is around 700 millivolts. Now, for the base collector, for it to be reverse biased, the P-type base must have negative voltage, while the N-type collector must have the positive voltage. That means the base voltage should be lower or smaller compared to the collector voltage. And if you get the voltage drop between the base and the collector, you should be getting a negative voltage. Okay, again, is it clear? Can you follow so far?
Yes, po.
Yes po, sir.
Thank you. How about the others? Nakakasunod
Yes,
ba?
sir.
Okay.
Yes po, sir.
Sige, thank you. Okay, let's continue. So since the base emitter junction is forward biased, we have an applied voltage. So the current flowing through that forward bias is what we call drift current. And since the current will be coming from the P-type, this is specifically a whole drift current. While on the other hand, the base collector is reversed biased. So the type of current flowing from the emitter and going out of the collector will be the diffusion current. Specifically, since it is coming from an N plus emitter going out on the N-type collector, the majority of the current would be an electron diffusion current. Okay, just in case you want to know what type of current are flowing inside the bipolar transistors. So that ends our discussion on the structure. Now let us continue on the currents and voltages. So let us put here our notations so that we will have a common notations, how to represent, how to indicate the currents and voltages of bipolar transistors. So here are the two symbols of bipolar transistors. We have here the NPN. You have the collector, base, and the emitter. Take note of the arrow in the emitter. For the NPN, the arrow is moving or pointing outwards. And we have here the symbol for the PNP. Again, this is the collector, base, and the terminal with the arrow is the emitter. And for the PNP, take note that the arrow is pointing inwards, pointing into our device. So for the currents, for the NPN, following the arrow direction, emitter current will be, in this example, will be flowing downwards. And since emitter current is the total current, then the collector current and the base current will be flowing into the transistor. Right? So emitter current is the total of collector current and the base current. So again, since emitter current is going out, then collector current and base current should be going in to the NPN. Okay? Then another equation for our current, you can use collector current is equal to beta times IB, where beta is the current gain. Okay? So do not forget this equation. IE equals IC plus IB. Emitter current equals collector current plus base current. And collector current equals current gain beta times base current. For the voltages, this is our notation. So the voltage between base and emitter would be the VBE with positive on the base and negative on the emitter. So whenever we use a two-letter voltage notation, the first letter indicates the positive potential. Then the second letter indicates the negative potential. So when you write a voltage VCB, it means that the positive is on the collector and negative on the base. And when you write VCE, that means you have positive on the collector and negative on the emitter. So VBE can be calculated using base voltage minus emitter voltage. Collector base voltage can be computed using collector voltage minus base voltage. And VCE can be computed using collector voltage minus the emitter voltage. Now for the PNP transistors, we have to alter the direction of the current. So this time, the emitter current is going into the device and the collector current and the base current are going out of the device. But the transistor current still applies. IE is still the total of IC plus IB. And we can still apply the current gain equation. So still IC is beta times IB. Then in terms of the voltages, emitter is now more positive. So we properly indicate it as VEB, positive on the emitter and then negative on the base. And then between base and collector, base is more positive. So we have to indicate VBC, positive on base, negative on the collector. And for the voltage between collector and emitter, it would now be VEC, with emitter being more positive or higher compared to the collector. So we can compute VEB as VE minus BB. VBC equals VB minus BC. And VEC equal to VE minus BC. Alright, nasusundan ba so far? Please confirm.
Yes po,
Yes,
sir.
sir.
Alright, sige, thank you. So again, we have here the NPN, bipolar transistors in the active mode. So note that bipolar transistor is operated in the active mode for amplification, for amplifier circuits. And in the active operation, the base emitter junction is forward biased and the base collector junction is reverse biased. And for the forward bias, recall that a positive voltage is applied at P-type and the negative voltage at N-type. While reverse biased, we have positive voltage at N-type and negative voltage at the P-type. So for the NPN, for us to operate this in the active mode, the base emitter must be forward biased. And since base is P-type, emitter is N-type, the base voltage must be higher or larger compared with the emitter voltage for it to be properly forward biased. While the base collector junction is reverse biased when the N-type collector is more positive compared on the P-type base. So the collector voltage must be larger than the base voltage. So in summary, the NPN is operating in the active mode when the collector voltage is higher than the base voltage and the base voltage is higher than the emitter voltage. Okay, is this clear?
Yes po, sir.
Sige, thank you. For the PNP, it still applies. For it to be in the active, base emitter must be forward biased. But since the layers are opposite type, you now have P-type emitter, N-type base, P-type collector. So the emitter voltage must be more positive. So it must be larger than base voltage. And for base collector to be reversed biased, the negative type base must be more positive compared on the P-type collector. So the base voltage must be larger than the collector voltage. All right. So in summary, the PNP is operating in the active mode when the emitter voltage is higher than the base voltage and base voltage higher than the collector voltage. All right, so that ends our notations for the currents and voltages of bipolar transistors. So let us now continue on the large signal or on the DC model of bipolar transistor. So this will describe the behavior or characteristics of bipolar transistors whenever we apply DC voltages. Okay. So here is the large signal model of NPN transistors. This is the symbol, and this will be the equivalent circuit. The NPN transistor behaves like a voltage-dependent current source connected between the collector and the emitter. So between the collector and emitter, we can visualize as having a current source. So the current will be the collector current, and the collector current will be dependent on the exponential of the input base emitter voltage. So this is our equation. Collector current is equal to IS times the exponential of VBE over BT. And then between the base and emitter, so since this is forward biased, we will have a forward biased PN diode. So between base and emitter, you have a forward bias diode with a voltage drop of VBE. So depending on the input VBE, we need to first turn on the junction, the diode between the base and emitter. Then after having an input current, we'll have the output current, okay, collector current. So the NPN transistor behaves like a forward biased base emitter diode and a VBE dependent current source from collector to the emitter. Okay, is this clear so far?
Yes, sir.
All right. So this is the model or the equation for the NPN or for any bipolar transistors. You have IC equals to IS times exponential of VBE over BT, where IC is the collector current, IS is the saturation current, VBE is the base emitter voltage, and VT is the thermal voltage. So the saturation current is defined by this model or equation. IS is equal to A sub E times Q times D sub N times the square of Ni divided by N sub B times WB. Again, IS is saturation current. A sub E is the area of the emitter. So the larger the emitter area, the higher the saturation current, the higher the collector current. Q is the charge of a single electron, equal to 1.6 times 10 to the negative 19 coulomb. D sub N is the diffusion constant of electrons. N sub I is the intrinsic concentration of the semiconductive material of bipolar transistor. N sub B is the doping concentration of base region. So based on this, the lower the doping concentration, the better. No? So when you have lower doping for the base region, you have higher saturation current, resulting to a higher collector current. Also, WB is the width of base. The smaller the width of base, the thinner the base region, the higher the saturation current, and the higher the collector current. Okay? Then VT is the thermal voltage that can be computed using this KT over Q, where K is the Boltzmann constant equal to 1.38 times 10 to the negative 23 joules per Kelvin. Q, again, is the charge of electron equal to 1.6 times 10 to the negative 19 coulomb. And T is the temperature expressed in Kelvin. So if the given is in Celsius, we will add 273 to convert it into Kelvin. And the result will be in terms of volts. Okay, is this clear? Again, please confirm.
Yes po, sir.
Okay, sige. Nasusundan nyo pa?
Yes po.
Okay, sige. Thank you. So, i-jot down nyo lang later on yung mga equations. No? Gagamitin natin yan when we analyze amplifier circuits. So, continuing on the large signal model of NPN transistors. So, again, this is our NPN, and this is the behavior of the bipolar transistor. Again, it behaves like a voltage-dependent current source and as a forward bias diode on the input side. So I did some simulations I plotted the collector current versus the input VBE. I set the saturation current to 10 femtoamperes, and I set the thermal voltage equal to 25 millivolts, and try to vary the base emitter voltage from 500 millivolts to 900 millivolts. So at lower VBE, you have a very low collector current, and at some point, the collector current will exponentially increase. So starting at 700 millivolts, the collector current is 14.46 milliamperes. And as we increase the input VBE, we expect that the collector current will increase exponentially. All right? And then, if we plot the collector current versus the VCE, again, using the same parameters, IS is 10 femtoamperes, VT is 25 millivolts, and this time, the VBE is taken at 700 millivolts. So, as we vary the VCE, the collector current remains at 14.46 milliamperes at any value of VCE. Since if you look at the model or at the equation, collector current is only affected by VBE. This is the only circuit parameter that can affect the circuit collector current. IS is a device parameter, so it depends on the transistor semiconductor, and VT would depend on the temperature. So it is only the VBE, which is a circuit parameter, that can affect the circuit parameter, which is the collector current. Now, in order to describe the effect of the VCE, we have to include the so-called early effect in bipolar transistors. So early is a name of the engineer who was able to observe this phenomenon in bipolar transistor. So his name is James Early, Engineer James Early. So we call the phenomenon as James Early effect, or simply early effect. Okay, and how does it go? So this is the principle behind the early effect. So again, the bipolar transistor will have forward biased base emitter junction and a reversed biased base collector junction. So the amount of reversed bias, that is the voltage between the collector and base, will be equal to, so if you get a voltage loop, it would be VCB plus BCB minus BCE, and then plus BBE equal to 0. So we can calculate the reverse voltage in terms of the circuit parameter. So you'll have VCE minus VBE. So this time, you now have VBE and VCE affecting the reverse bias. So looking closely on the reverse bias junction, on the reverse bias, again, we have the depletion region. And the orange part is the layout base width. The effective base width is affected by the depletion region. So when the reverse bias increases, the depletion region will widen, will increase, and this will decrease the effective base width. So yun yung na-observe ni early effect, no? Yun yung principle na sinasabi niya, no? So as you increase the reverse bias BCB, it will widen the depletion region and it will decrease the effective base width. Okay? And when the WB decreases, pag bumaba yung WB because of the reverse bias, the collector current will increase. Yun yung tinatawag natin na early effect. Okay? So the early effect is described as the applied reverse bias across the base collector junction, that is the BCB, affects the width of the depletion region, the effective base width, and eventually the collector current. So this was discovered by James Early. So for example, when the VCE increases, so pag lumaki yung voltage between the collector and the emitter, this will also increase the reverse bias BCB. And when reverse bias increases, the width of the depletion region will also increase. And this will reduce the base width. And when WB decreases, the collector current will increase. Nasundan ba yung early effect? Please confirm. Paki-confirm if you can follow the early effect.
Yes po.
Okay, sige. Thank you. How about the others?
Yes po, sir.
Sige, thank you. So we will now modify our model or equation, this time incorporating the early effect. So we will now have additional parameter. So the model will now be IC equal to IS times the exponential of VBE over BT, all multiplied by the quantity 1 plus BCE over VA. So again, the model is represented by the forward biased base emitter diode, and this time you now have VBE and VCE dependent current source. So the model is now IC equal to IS, exponential of VB over BT, all multiplied by 1 plus BCE over BA. So IC is collector current, IS is saturation current, VBE is base emitter voltage, VT is thermal voltage, VCE is the collector emitter voltage, and VA is the early voltage. So in case VA is assumed to be infinite, then we will be ignoring the early effect. All right, VCE divided by infinity would be equal to almost zero. So we will be returning to our simple model. Okay, but when there is a given value for the early voltage, this will be our large signal model for the NPN. So I tried to plot again the large signal model, this time with the early effect. So as for IC versus VBE, it's still the same. But as for IC versus BCE, when VCE changes, this time the collector current also changes. Okay, so since IC is now being affected by VCE. Okay, klaro ba yung ating model? Please confirm.
Yes po, sir.
All right, sige. So pakisulat nyo yung equation na yan, no? Gagamitin natin later on. So for the PNP transistors, the behavior would be similar, but we just need to adjust the direction of the diodes, adjust the voltage notation, the direction of the current source, and the notation for the voltages. But essentially, they are the same with the NPN. Okay, so we still have IC equal to IS times exponential of voltage drop at the input junction divided by the thermal voltage. And for the early effect, we just have to adjust the notation for the emitter collector voltage. All right, that ends our large signal model for bipolar transistor. So let us continue with the characteristics of bipolar transistors. So we have the input characteristics. So this pertains to the base current affected by the VBE. So what will happen to the base current when we vary or change the base emitter voltage. So this is our test circuit. You have the NPN with the base resistor, collector resistor, and the emitter resistor. Then we have the base voltage indicated by VBB. And we have the collector supply indicated by VCC. And we are going to do the operating point. We set the operating temperature to 27 degrees Celsius. And we are going to do a DC simulation, changing the base supply from 0 to 20 volts with an increment of 0.50 volts. So we have here the VBE, and this is the base current. And this is the simulation results using the LT Spice. So as we change the VBE, the voltage between the base and the emitter from 0 millivolts to supposedly VBB is from 0 to 20. But if we only get the voltage right at the base and emitter terminal, we can see that VBE will only be up to less than 900 millivolts. No? Hanggang dito lang. So nagiging almost constant na siya. Then we try to measure or plot the base current. So here we can see that base current is also an exponential function of the VBE. We need to forward bias the PN junction before we can have the input base current. So the forward bias voltage would be around 700 millivolts. But when we do simulations, when we do calculation, sometimes the turn-on voltage or the forward bias voltage can be lower than 700 millivolts. Or sometimes it could be higher, depending on the device parameters. Okay? Ang default lang natin 700. But hindi laging 700. No? Pwedeng mas mababa or mas mataas. So it is around that value. Okay, so we plotted using this equation. So this is IC. IC is equal to IS. All right, times the exponential function multiplied by the early voltage or early effect. So we substitute IC in terms of IB. So we can have the IB equal to 1 over beta times the IS times exponential function times the early effect. Then we also have the output. We have here the transfer characteristic. So when we say transfer, we refer to output current versus input voltage. So again, we have the same test circuit. Again, we'll be varying the base voltage from 0 volt to 20 volts with an increment of 0.50. And we are going to monitor the input VBE and the resulting collector current. So the output IC versus input VBE also yields the exponential function. Okay? So this follows this model. No? Ito pa rin yung model natin. We can have another transfer characteristics that is output current versus the input current. So IC versus IB. So you have input IB versus the output IC. So when we do the simulation, under the lower base current, the base current is proportional with the collector current. So the slope will be dependent on the current gain. So again, IC is equal to beta IB. And then at some point, the collector current will reach the saturation value. So even though we further increase the input current, the collector current will remain almost constant. So at this point, the transistor is in the saturation. While from this point up to here, the transistor is in the active mode. Okay? So this active mode or the linear region, it follows IC equal to beta IB. Then on this region, you now have the saturation, wherein collector current remains almost constant, since the VCE is constant. Okay, so that's why collector current remains constant. Excuse me. All right. Then we continue on the small signal or AC model of bipolar transistors. What is the characteristic or what is the behavior of bipolar transistors when we apply alternating current or alternating voltages? So here is the small signal model of NPN transistors. So here is the symbol, and this will be the equivalent circuit. All right? So between base and emitter, you have the forward bias input resistance, denoted by R pi. All right? So R pi can be calculated using current gain beta divided by transconductance GM. And the voltage drop between the base and emitter is VBE, or can also be denoted as V pi. Okay, so VBE and V pi are the same. Then, from collector to the emitter, we have here the current source. You have the ideal current source in parallel with the output resistance. So the current source is the IC, equal to the transconductance GM times the input voltage V pi. Again, V pi is the voltage between base and emitter. Then, in parallel with the current source, we have the output resistance between the collector and emitter. And it can be calculated using early voltage divided by the DC operating collector current. Okay. So this is the behavior of bipolar transistors. Excuse me. So you have the forward bias resistance from base to the emitter. Then we have the VBE dependent current source from collector to the emitter, and we have the reverse bias resistance from collector to the emitter. So the small signal parameters of NPN transistors are, you have GM, we also have R pi, then we also have RO or R out. So for GM, equation is operating collector current. So this is the DC operating collector current divided by the thermal voltage. All right, so GM is the transconductance equal to operating collector current divided by the thermal voltage. Another parameter is R pi, equal to current gain beta divided by the transconductance GM. And RO, or output resistance, or collector emitter resistance, can be calculated using early voltage divided by the operating collector current. So these are the three small signal parameters of NPN transistor: GM, R pi, and R out. All right, na susundan ba? Please confirm.
Yes, sir.
Sige.
Yes.
Again, paki-note nyo yung mga equations. Paki-copy nyo yan. So regarding the transconductance of bipolar transistors, I did some simulations, and we can see the collector current versus the VBE. Right? So we run a transient simulation for 3 milliseconds. So we have a DC voltage on the input. Then at this point, the AC is 0. So purely DC pa lang to. No? So we can see that when there is a constant VBE, collector current is also constant. So note that AC component of input is 0 millivolts. So this is essentially a DC simulation. So VBE, DC is 827.32 millivolts. And the operating collector current is 0.404 milliamperes. Now this time, we added an AC signal, 20 millivolts. So the 20 millivolt sine wave is reflected on the VBE. Okay, we can notice that there is a 20 millivolts on the VBE. And any changes on the VBE will also produce changes on the output collector current. Alright, so nakita mo yung collector current, nagkaroon din ng sine wave. So you have the point, based on the measurements, we have the 0.16 millivolts peak to peak for the VBE, and that results to 10 microampere peak on the collector current. So that is the transconductance. For every 0.16 millivolts, the collector current will have 10 microampere change. Okay, yun yung transconductance natin. So you have the change in VBE will result to a change in the collector current. So delta VBE will result to delta IC. So GM is equal to the change in the collector current for a given change in VBE. So if we substitute the IC, so you have the derivative of IS exponential of VB over BT divided by the derivative or change in the VBE, this would result to this equation. So GM is 1 over VT times IS exponential of VBE over BT. Wherein IS exponential of VB over BT is IC over BT. So that is how we were able to derive the equation for the transconductance. All right, so GM equal to IC over BT is derived on the effect of VBE on the collector current. Okay, nasundan ba yan?
Yes,
Please confirm.
sir.
Sige. For the PNP, we just have to adjust the notations. All right, so take note of the direction of the current source. So the collector current must be going out of the collector terminal. All right, so yun lang yung difference nung NPN tsaka PNP model. Okay, so I think that ends our discussion for today. Any questions so far?
None po.
All right, sige, thank you.